Picture a place where the laws of physics stretch to their breaking point, where a single teaspoon of matter weighs as much as a mountain, and magnetic fields are strong enough to rip atoms apart from thousands of miles away. This isn't science fiction, it's the reality of neutron stars, some of the universe's most extreme and enigmatic objects. Born from the explosive deaths of massive stars, these cosmic powerhouses pack the mass of our entire sun into a sphere no wider than a city, spinning faster than a blender blade and shining with unimaginable intensity. And yet, despite their ferocious energy, many of them lurk in the farthest, darkest reaches of space, hidden from plain sight and brimming with secrets waiting to be uncovered. What makes these distant neutron stars so fascinating isn't just their mind-bending physics, though that alone could fill volumes, but the sheer scale of mystery they represent. Imagine a stellar graveyard where the remnants of dead stars pulse like celestial lighthouses, sending beams of radiation across the cosmos that flicker with eerie precision. Some of them race through space at speeds that defy logic, while others harbor magnetic fields so intense they could strip the data from every credit card on Earth in an instant. And here's the thing, the more we learn about these objects, the more questions they seem to create. How do they form? What exotic matter hides in their cores? Could they hold clues to the very fabric of space and time? That's exactly what we're diving into today, 30 astonishing facts about the universe's most distant neutron stars, from their cataclysmic births to the bizarre phenomena they unleash across the cosmos. We'll explore how these stellar zombies defy everything we thought we knew about density, gravity, and even the limits of matter itself. You'll discover why some neutron stars act like cosmic magnets a trillion times stronger than anything on Earth, and how others might be quietly shaping the galaxies around them in ways we're only beginning to understand. So buckle up, because by the time we're done, you'll never look at the night sky the same way again. To understand how neutron stars come into existence, we have to witness one of the universe's most violent events, the death of a giant. When a star at least 8 times more massive than our Sun exhausts its nuclear fuel, it doesn't fade quietly. Instead, it dies in a cataclysmic explosion known as a supernova, unleashing in mere seconds the energy of a billion suns. But the real magic happens in the chaos of that destruction. As the outer layers blast outward in a blinding flash, the star's core, no longer supported by nuclear fusion, collapses inward at nearly a quarter the speed of light. Under this unimaginable pressure, atoms are crushed beyond recognition. Electrons and protons merge, forming a sea of neutrons so densely packed that a single sugar cube's worth of this material would weigh more than Mount Everest. The entire core, now just a sphere about 12 miles across, contains the mass of our entire sun squeezed into the footprint of a city. That's a density so extreme that if you could scoop up a teaspoon of neutron star matter, it would outweigh every car, every building, and every person on Earth combined. Yet this staggering compression isn't even the most mind-bending part. The forces at work here are so strong that they warp the rules of physics as we know them. Gravity isn't just intense, it's so overpowering that if you dropped an object from just a meter above the surface, it would slam into the ground at millions of miles per hour. And inside that ultra-dense core, matter might be squeezed into forms we can't even replicate in labs, exotic states where neutrons themselves break down into a soup of quarks or stranger, theoretical particles. What's left after this cosmic demolition derby is a neutron star spinning furiously, sometimes hundreds of times per second, and glowing with the pent-up energy of its explosive birth. But here's the kicker, these extreme objects aren't rare flukes. Astronomers estimate that the Milky Way alone harbors hundreds of millions of them, relics of massive stars that burned bright and died young. And the most distant ones, lurking in the far corners of galaxies or even drifting in the void between them, carry secrets about the universe's most extreme conditions, conditions so harsh they make black holes look almost tame by comparison. If you thought the speed of a jet engine or a hummingbird's wings was impressive, neutron stars will shatter every benchmark you've ever known. These cosmic powerhouses don't just spin, they whirl at rates so dizzying they defy comprehension. Take Pulsar J 1748-2446 AD, the current record holder, which completes a jaw-dropping 716 rotations every single second. At that speed, its equator is moving at nearly a quarter the speed of light, so fast that if it spun just a tad quicker, the star would tear itself apart from centrifugal force. To put that in perspective, if Earth rotated that rapidly, a day would last less than the blink of an eye, and everything on the surface would be hurled into space. But how does something with the mass of a sun manage to spin like a hyperactive top? It all comes down to conservation of angular momentum, the same physics that makes an ice skater spin faster when they pull their arms in. When a massive star collapses into a neutron star, its original rotation gets concentrated into a sphere thousands of times smaller. Imagine a figure skater starting a slow turn with arms outstretched, then suddenly shrinking to the size of a grape. Their rotation would become a blur. That's exactly what happens during a supernova, turning a star that might have rotated once every few weeks into a celestial speed demon spinning hundreds of times per second. This extreme rotation isn't just a curiosity, it's the engine behind one of the universe's most mesmerizing phenomena, pulsars. As a neutron star spins, its insane magnetic field, trillions of times stronger than Earth's, channels radiation into narrow beams shooting from its magnetic poles. If those poles aren't aligned with its rotation axis, the beams sweep across space like a cosmic lighthouse. Every time one of these beams points at Earth, we detect a pulse of radiation, sometimes with a regularity more precise than atomic clocks. The Crab pulsar, for instance, flickers 30 times a second with such perfect timing that early researchers jokingly nicknamed its radio signals, LGM-1, for little green men, until they realized they were witnessing nature's most accurate metronome. What's truly astonishing is how these rapid spins change over time. Younger neutron stars often rotate at breakneck speeds, but they gradually slow down as their magnetic fields sap energy, acting like cosmic brakes. Some, however, get a second wind like millisecond pulsars, ancient neutron stars revived by siphoning material from a companion star. These rejuvenated objects can spin even faster than their younger counterparts, reaching speeds that push the limits of physics. And in the most extreme cases, their rotations might even ripple space-time itself, sending gravitational waves whispering across the cosmos, a silent testament to the sheer power of these celestial dynamos. The surface of a neutron star isn't just hostile, it's a place where gravity rewrites the rules of reality. Here, the pull is so intense that dropping an object from waist height would send it crashing down at speeds rivaling a meteor strike. Picture this: a marble released just 1 meter above the surface would accelerate to millions of miles per hour before impact, hitting with the energy of a nuclear bomb. That's because the gravity on a neutron star's surface is around 100 billion times stronger than Earth's, a force so extreme it doesn't just bend space-time, it twists it into knots. This isn't theoretical. Einstein's general relativity predicted exactly this kind of gravitational insanity. Near a neutron star, space isn't just curved, it's stretched like taffy, creating a lensing effect so pronounced that light from the star's far side gets bent around its circumference, making the entire surface visible from certain angles. Imagine standing on one and looking up. Instead of a black sky, you'd see a distorted panorama of the star's own glowing surface wrapping around you, a funhouse mirror built by gravity itself. Even photons, particles of light that usually zip through the cosmos unimpeded, get yanked back toward the surface like they're climbing an endless hill. But the real magic happens when this gravity interacts with matter. gas and dust spiraling toward a neutron star don't just fall. They get shredded into plasma and accelerated to near light speeds, creating searing hotspots that glow with X-rays. Some neutron stars, like the famous Scorpius X1, shine brighter in X-rays than 100,000 suns, all because of the raw power of their gravity converting infalling material into pure energy. And if two neutron stars orbit each other, their gravitational dance sends ripples through space-time itself, vibrations we've detected as gravitational waves here on Earth. What's truly humbling is how these cosmic extremes force us to rethink the very nature of reality. On a neutron star, gravity isn't just a force, it's a sculptor, bending light, warping time, and compressing matter into forms that challenge every law we've ever written. And somewhere in that gravitational madness, hidden in the equations of relativity, might lie clues to how the universe itself was woven together. If you think the sun is hot, neutron stars laugh in the face of solar temperatures. These cosmic remnants don't just get warm, they reach temperatures so extreme they make the sun's core feel like a winter breeze. At birth, a neutron star's surface blazes at around 1 million degrees Kelvin, hotter than the center of our own star. But here's the twist. While the sun's heat comes from ongoing nuclear fusion, a neutron star's furnace runs on the leftover energy of its catastrophic collapse, simmering like a dying ember that somehow burns brighter than the fire that created it. What's truly mind-blowing isn't just the raw temperature. It's how these stars manage to stay so blisteringly hot despite being tiny and isolated. A spoonful of neutron star matter holds enough heat to vaporize an entire city, yet these objects are only about 12 miles across. With so little surface area, you'd expect them to cool rapidly, like a glowing coal shrunk to the size of a pebble. But neutron stars defy intuition. Their insane density traps heat like a thermos from hell, slowing the cooling process to a crawl. Some retain surface temperatures in the hundreds of thousands of degrees for millions of years, glowing fiercely long after their explosive births. And that heat isn't just sitting there, it's screaming across the cosmos in the form of X-rays and gamma rays. While visible light barely escapes the star's crushing gravity, these high-energy photons punch through, creating signatures so distinct we can spot them from thousands of light-years away. Take XTJ 1810-197, a neutron star whose X-ray emissions suddenly flared to 10 times their normal brightness, catching astronomers' attention like a cosmic alarm bell. Or Geminga, a silent killer in the constellation Gemini, pumping out gamma rays with enough energy to strip electrons from atoms light-years distant. But the real mystery lies beneath the surface. While the outside burns at a mere million degrees, simulations suggest the core might be a cauldron of quark-gluon plasma, a primordial soup hotter than the universe a millisecond after the Big Bang. This isn't just heat, it's a relic of creation itself, trapped inside a stellar tomb and radiating echoes of a time when matter itself was unrecognizable. And every X-ray we detect is a whisper from that hidden inferno, a clue to forces beyond anything we can replicate on Earth. Even the most precise cosmic clocks sometimes stumble, and when a pulsar suddenly speeds up for no apparent reason, astronomers take notice. These mysterious hiccups, known as glitches, defy the steady slowdown we expect from aging neutron stars. Imagine a spinning top gradually losing speed, only to inexplicably lurch faster mid-spin. That's the enigma pulsars present when their rotations abruptly jump by fractions of a second, sometimes gaining hundreds of extra spins per year in an instant. The Vela pulsar, one of the most active glitches, has racked up over 20 of these events since its discovery, each one sending shockwaves through our understanding of stellar interiors. So what's jolting these ultra-dense objects into sudden overdrive? One leading theory points to starquakes, cosmic tremors rippling through the neutron star's rigid crust. Picture Earth's tectonic plates, but on a surface 100 trillion times stiffer. where even microscopic cracks release energy equivalent to a magnitude 23 earthquake. When the star's crust fractures under immense stress, the entire structure might contract slightly, like a figure skater pulling their arms tighter. And just like the skater, that tiny shift could make it spin faster. But there's another, far stranger possibility lurking beneath the surface: superfluid vortices. Deep inside a neutron star, conditions are so extreme that neutrons might flow without friction, creating whirlpools of quantum chaos. Normally, these vortices align with the star's rotation, but if they suddenly break free from the crust's grip, their pent-up energy could transfer to the surface in a rotational speed boost. It's like a jar of honey suddenly turning liquid. The inner turmoil spills outward, giving the whole system an unexpected kick. What baffles scientists most isn't just the glitches themselves, but their unpredictability. Some pulsars glitch regularly like clockwork, while others stay silent for decades before lurching without warning. The Crab pulsar, for instance, has clocked only a handful of minor glitches since its discovery, while others behave like unruly engines, sputtering with erratic bursts of acceleration. Each event leaves behind a forensic trail: a slight change in rotation rate, a flicker in electromagnetic emissions, clues that might one day reveal what's really churning in the hearts of these stellar undead. And here's the kicker: glitches might be more than just cosmic curiosities. By studying them, we're essentially performing ultrasound on neutron stars, using their rotational stumbles to map the exotic physics hidden beneath surfaces no probe could ever reach. Every hiccup peels back another layer of mystery, hinting at quantum behaviors so extreme they defy laboratory replication. In that sense, these hyper-dense corpses aren't just dead stars. They're living experiments, broadcasting secrets from realms where matter itself wears unfamiliar faces. When we think of mountains, we picture towering peaks scraping the sky, but on a neutron star, even the tiniest bump becomes a marvel of cosmic proportions. These ultra-dense spheres, famous for their near-perfect smoothness, actually sport surface irregularities so minuscule they'd be invisible to the naked eye. We're talking about deformations barely a few millimeters tall, yet in the extreme gravity of a neutron star, these microscopic mountains carry the weight of entire Himalayan ranges. Picture this: a bump the height of a pencil tip, pressed into a surface where every square centimeter weighs billions of tons. That tiny imperfection strains against gravity with the energy of 1,000 nuclear bombs, warping space-time itself. These minuscule distortions might sound trivial, but they're anything but. The intense gravitational field amplifies their impact, making even atomic-scale imperfections ripple outward as gravitational waves. The same ripples in space-time predicted by Einstein and detected by observatories like LIGO. When a neutron star with these deformations spins, its mountains and valleys churn space-time like a spoon stirring honey, sending faint but detectable tremors across the cosmos. The faster the spin, the more pronounced these waves become, creating a signature hum that sensitive instruments can pick up light years away. What's truly astonishing is how these mountains form in the first place. Unlike Earth's peaks sculpted by tectonic collisions, neutron star mountains arise from the crust's mind-bending physics. The surface, a crystalline lattice of iron nuclei packed tighter than bullets in a firing line, can crack under unimaginable pressure. Magnetic fields billions of times stronger than Earth's twist this crust like taffy, while rapid rotation flattens the star slightly at the poles. These forces create stresses that buckle the surface, leaving wrinkles no taller than a grain of sand but dense enough to distort the fabric of reality around them. Detecting these gravitational whispers isn't just about proving Einstein right. It's a window into the star's hidden structure. Each ripple encodes information about the crust's composition, the core's mystery matter, and even the strength of the magnetic fields buried beneath. Some theorists speculate that extreme mountains could form during starquakes, when the crust shatters and rebounds, momentarily creating mile-high distortions before gravity smashes them back down to millimeter scale. Others suggest certain neutron stars might sustain larger deformations if their magnetic fields freeze the crust into rigid, uneven shapes, like cosmic fingerprints pressed into the surface of spacetime. The hunt for these gravitational fingerprints is already reshaping astronomy. When LIGO catches a neutron star's telltale spacetime vibrations, it's not just hearing a distant spin, it's mapping the topography of an object where gravity turns imperfections into cosmic gongs ringing across the universe. And with every faint pulse detected, we're one step closer to answering a tantalizing question. What other secrets are written in the tiny, impossible mountains of the universe's most extreme objects? Among the already extreme inhabitants of the cosmic zoo, Magnetars stand out as the undisputed champions of magnetic madness. These neutron stars don't just have strong magnetic fields, they wield forces so powerful, they distort the very structure of atoms themselves. Imagine a magnet so intense it could erase every hard drive on Earth from halfway across the solar system, or pull the iron from your blood at a distance of 100,000 miles. That's the reality of a magnetar, a neutron star with a magnetic field a quadrillion times stronger than Earth's, turning the space around it into a nightmare of twisted physics. These fields don't just bend the rules, they obliterate them. In normal conditions, electrons orbit atomic nuclei in predictable patterns, but near a magnetar, the magnetic force is so overwhelming it stretches atoms into needle-thin rods, warping electron clouds into bizarre, elongated shapes. This phenomenon, called magnetic splitting, effectively shreds the chemical bonds that hold matter together, rendering chemistry as we know it impossible. A hydrogen atom drifting too close wouldn't just ionize, it would unravel like a thread caught in a cosmic shredder. But the real fireworks happen when these fields shift. Magnetars don't sit quietly, their crusts, frozen into rigidity by unimaginable pressures, occasionally crack under the strain of their own magnetism. These starquakes release energy equivalent to 1 billion megaton bombs, triggering gamma-ray flares so bright they temporarily outshine entire galaxies. In 2004, a magnetar 50,000 light-years away unleashed a blast that ionized Earth's upper atmosphere despite being halfway across the Milky Way. Another, SGR 1806-20, produced a flare in 2004 that, for a fraction of a second, outshone the full moon, all from an object smaller than Manhattan. What's terrifying isn't just their power, but their unpredictability. Unlike pulsars with their metronomic precision, magnetars erupt without warning, their surfaces heaving like frozen lakes under impossible stress. And when they do, they don't just emit light, they flood space with X-rays, gamma rays, and even antimatter, creating lethal bubbles of radiation that would sterilize any nearby planetary system. Yet paradoxically, these apocalyptic events might also seed the cosmos with heavy elements, forging gold, platinum, and uranium in their violent wakes, a reminder that even the universe's most destructive forces can be creators in disguise. Hidden beneath this magnetic fury lies an even deeper mystery: how these fields form in the first place. One theory suggests that when a neutron star is born from a particularly fast spinning core, its interior becomes a dynamo of swirling neutrons and protons, amplifying its magnetic field to ludicrous levels. Others propose that magnetars might start as unusually massive neutron stars whose gravity crushes their magnetic fields into ever tighter configurations, like squeezing a balloon until the pressure becomes unsustainable. Whatever the cause, the result is a celestial monster, one that reminds us just how strange and violent the universe can get when physics pushes matter to its breaking point. In the darkness between galaxies, a cosmic bomb detonates without sound, an explosion so fierce it dwarfs every star in the Milky Way combined. This isn't the birth of a black hole or the collision of galaxies. It's a magnetar flare, a fleeting tantrum from one of the universe's most volatile objects, capable of unleashing in half a second what our sun would take 100,000 years to produce. The numbers defy reason. A single eruption can blast out enough energy to power human civilization for billions of years, all from an object smaller than a city. What makes these outbursts even more astonishing is their sheer reach. While most cosmic events fade into obscurity beyond a few million light-years, magnetar flares punch through the universe like interstellar foghorns. In 2004, astronomers witnessed one such eruption from 50,000 light-years away, a flare so intense it bounced off the Moon and lit up Earth's upper atmosphere, momentarily altering its conductivity. Another, spotted in 2020, came from 13 million light-years distant in the galaxy Messier 82, yet its gamma-ray signature was unmistakable, cutting through cosmic noise like a supernova's flashbulb. To grasp the scale of this energy, imagine comparing a candle to the world's entire nuclear arsenal. If the sun's total output over a century were that candle, a magnetar flare would be every warhead detonating simultaneously, a fireball visible clear across the observable universe. These aren't just stellar flares, they're hyper-violent reconfigurations of magnetic fields, where pent-up energy snaps like an overwound spring, hurling particles to near-light speeds. The resulting gamma rays carry enough punch to strip electrons from atoms light-years away, creating expanding bubbles of ionized gas that linger for centuries. Yet for all their fury, these eruptions are blink and you'll miss it affairs. Lasting anywhere from milliseconds to a few minutes, they're cosmic ephemera here and gone before most telescopes can swivel to look. That transience makes them doubly precious to scientists. Each flare is a laboratory for physics under conditions we can't replicate. Magnetic fields strong enough to distort quantum vacuum, temperatures rivaling the universe's first second, and accelerations that hurl matter faster than any human-built machine. What's left after the fireworks show fades? Sometimes nothing but a slightly calmer magnetar, its magnetic field reconfigured like a shuffled deck of cards. Other times, the star emerges permanently altered, its crust fractured, its rotation jolted, its outer layers vaporized into a temporary corona of superheated plasma. And floating outward into the void, invisible but inescapable, are the echoes of that energy, ripples in space-time, gusts of charged particles, and a silent testament to the fact that sometimes the universe's smallest things pack the biggest punches. Neutron stars don't just push the limits of physics, they rewrite the rulebook entirely. These cosmic relics act as natural laboratories, creating conditions so extreme they're impossible to replicate in any Earth-bound facility. Imagine trying to study matter compressed to densities where atomic nuclei touch, or magnetic fields strong enough to distort the quantum vacuum itself. No particle accelerator or supercomputer can simulate these environments, yet neutron stars do it effortlessly, offering scientists a front-row seat to physics that would otherwise exist only in theory. One of the most tantalizing puzzles lies in their cores. Here, matter isn't just dense, it's crushed into bizarre, poster-like phases unimaginable anywhere else. Under pressures 100 trillion times Earth's, protons and neutrons rearrange into structures scientists poetically call nuclear poster. Picture sheets of nucleons flattened into lasagna layers or twisted into spaghetti like strands, all vibrating under gravitational forces that would snap steel like a dry twig. These configurations aren't just hypothetical, they may explain why some neutron stars cool slower than expected, their heat trapped in these quantum labyrinths like energy in a cosmic thermos. But the real breakthrough comes when we study how these stars interact with their surroundings. Take quantum chromodynamics, the theory governing how quarks and gluons behave. On Earth, testing it requires smashing particles at near-light speeds in machines like the Large Hadron Collider. But neutron stars are nature's own colliders, where the sheer weight of overlying material squeezes core matter so tightly that quarks might break free from their protons and neutrons, forming a primordial soup last seen microseconds after the Big Bang. Some theories even suggest the cores of the most massive neutron stars might harbor strange quarks, exotic particles that could turn the entire star into a single, gigantic atomic nucleus unlike anything in the periodic table. What makes these stars unparalleled labs isn't just their internal chaos, it's their visibility. Unlike black holes that swallow evidence, neutron stars broadcast their secrets. Their spin rates, surface temperatures, and even gravitational waves carry fingerprints of the physics at play inside. When a neutron star's rotation stutters during a glitch, it's like hearing the creaks and groans of a building's framework. Each vibration hints at the materials and forces holding it together. And when two neutron stars collide, the resulting fireball fuses heavy elements like gold and platinum in its wake, offering a live demonstration of cosmic alchemy that traces back to the very fabric of matter itself. Every X-ray pulse, every gamma-ray burst, and every ripple in space-time from a distant neutron star is a data point in an experiment set up by the universe, one we're only beginning to decode. By observing how these stars bend light, warp time, and even occasionally vanish behind their own gravity's lens, we're not just studying stellar corpses. We're peering into a realm where the fundamental laws of nature are stretched, twisted, and sometimes broken, a place where the answers might rewrite our understanding of reality itself. Neutron stars might seem like solitary wanderers drifting through the cosmos alone, but some of these extreme objects have partners in crime. Picture a cosmic dance where one partner is a super-dense stellar corpse, and the other could be anything from a humble red dwarf to another neutron star or even a black hole. These binary systems aren't just rare oddities, they're gravitational laboratories offering front-row seats to some of the universe's most spectacular collisions. Take the famous Hulse-Taylor binary discovered in 1974. Here, a neutron star and a pulsar orbit each other every 7.75 hours, their gravitational embrace so tight that the entire system could fit inside our sun. Over decades, astronomers noticed something extraordinary. Their orbit was shrinking. Each revolution brought them a few millimeters closer, not because of friction, but because they were radiating energy in the form of gravitational waves, ripples in space-time predicted by Einstein a century ago. This slow, inevitable spiral confirmed a startling truth. These stars were destined to collide, their fate sealed by the relentless pull of gravity. But how does this gravitational tango work? Imagine two skaters holding hands, spinning faster and faster until they're pulled into a final, crushing embrace. In space, that pull comes from the energy lost as gravitational waves, a process that, over millions of years, drags even the most distant pairs toward catastrophe. The closer they get, the stronger the waves, creating a feedback loop that accelerates their demise. By the final moments, their orbits shrink from years to milliseconds, and the resulting collision unleashes more energy in a few seconds than all the stars in the observable universe combined. These mergers aren't just violent, they're cosmic gold mines, literally. When two neutron stars collide, the extreme pressures and temperatures forge heavy elements like gold, platinum, and uranium in a process called rapid neutron capture. The kilonova explosion that follows sprays these precious metals across space, seeding future generations of stars and planets. In 2017, the LIGO and Virgo observatories detected gravitational waves from one such collision, while telescopes around the world caught the fiery afterglow, a landmark event that proved neutron-star mergers are the universe's ultimate alchemists. Yet the most fascinating binary systems might be the ones involving black holes. When a neutron star pairs with a black hole, it's a battle of extremes, an object where gravity is almost strong enough to resist oblivion, circling one where it's already lost. As the black hole's tidal forces stretch the neutron star into a teardrop shape, the star fights back with its own immense gravity, creating a spectacular death spiral. Sometimes the neutron star is swallowed whole, vanishing without a trace. Other times it's torn apart in a brilliant flare of X-rays and gamma rays, its material forming a glowing accretion disk around the black hole, a final, defiant blaze before being erased from existence. These cosmic duos remind us that even in the vast emptiness of space, nothing truly exists in isolation. And when neutron stars find companions, their stories become even more extraordinary, ending not with a whimper, but with a bang that echoes across the universe. Every piece of gold jewelry you've ever worn, every platinum ring, even the uranium-fueling nuclear reactors, all of it was forged in the heart of a cosmic catastrophe. These precious metals didn't form in the fiery cores of stars like our Sun. They were born in something far more violent, the collision of neutron stars, a spectacle so powerful it can briefly outshine entire galaxies. When two of these ultra-dense remnants spiral together, they don't just merge, they detonate in a fireball called a kilonova, scattering newly minted heavy elements across the cosmos like a celestial shotgun blast. Here's how the alchemy works. In the final moments before collision, the neutron star's immense gravity shreds them apart, creating a swirling maelstrom of neutrons hotter than the Sun's core. Normally, atomic nuclei capture neutrons slowly, building heavier elements step by step. But in this neutron-rich hellscape, nuclei are bombarded so rapidly they can't stabilize atoms, gorge on neutrons like starving diners, bloating into unstable isotopes that decay into gold, platinum, and other rarities. This rapid neutron capture process, or R process, is the universe's ultimate forge, running at speeds impossible in any other environment. The proof came in 2017, when astronomers witnessed a neutron star merger 130 million light-years away. The event, dubbed GW170817, sent gravitational waves rippling through Earth, followed by a dazzling kilonova flare. Spectrographs revealed telltale fingerprints of heavy elements in that light, particularly strontium, gold, and platinum, confirming what theorists had long suspected. Calculations suggest a single merger can fling up to 10 times Earth's mass in gold alone into space, enough to seed thousands of future solar systems with precious metals. But kilonovas aren't just about bling. They're cosmic recycling plants. The gold in your wedding band might have spent billions of years drifting between stars before our young solar system scooped it up. Uranium, essential for both nuclear power and weapons, owes its existence to these collisions. Even iodine, crucial for human thyroid function, is an R-process product. Without neutron star mergers, the periodic table would be missing its heaviest, most fascinating elements, and life as we know it might not exist. What's startling is how rare these events are. While supernova occur roughly once per century per galaxy, neutron star mergers might happen only once every 100,000 years in the same volume. That scarcity explains why gold remains precious not just on Earth but across the universe. Every time two neutron stars collide, they're essentially minting cosmic currency, scattering riches that might one day end up in a newborn planet's crust or around someone's finger. Yet the real magic lies in the aftermath. The ejected material doesn't just float aimlessly, it joins vast molecular clouds where gravity eventually gathers it into new stars and planets. Our own solar system likely condensed from a cloud peppered with debris from ancient kilonovas, meaning the gold in your jewelry isn't just stardust, it's the ashes of a cataclysm older than Earth itself. And somewhere out there, another neutron star duo is circling toward oblivion, ready to seed the universe with the ingredients for future civilizations. Even neutron stars, those nearly indestructible remnants of stellar explosions, aren't immortal. Given enough time or the wrong cosmic circumstances, these ultra-dense objects face a second death, one far quieter than their explosive birth. Picture a city-sized sphere of degenerate matter spinning silently in the void, its furious rotation gradually winding down like a cosmic top losing momentum. As its spin slows over billions of years, the outward centrifugal force that once helped counterbalance its own crushing gravity weakens. The star's relentless weight, already barely contained, begins winning the battle until one critical moment when the entire structure collapses inward, vanishing in an instant. No flash, no explosion, just space-time itself buckling under the strain as the neutron star crosses the event horizon and becomes a black hole. But spin decay isn't the only path to oblivion. Some neutron stars meet their end by cosmic gluttony. When orbiting a companion star in a binary system, they can slowly siphon off material, growing heavier with each stolen mouthful. At first, this accretion powers dazzling X-ray emissions, turning the neutron star into what astronomers call an X-ray binary. Yet there's a dangerous threshold around 2 to 3 solar masses where even degenerate neutron matter can't withstand the growing pressure. As the star tips past this limit, atoms collapse into a singularity mid-meal. One moment it's a pulsar blinking rhythmically, the next an invisible point in space where even light can't escape. The physics behind this transformation is stranger than fiction. Unlike supernova that announce their presence across galaxies, these quiet collapses happen without fireworks. Quantum tunneling effects might even allow some neutron stars to bypass their theoretical mass limits entirely, suddenly transitioning to black holes without warning, like a bridge giving way under a weight it's held for centuries. Others could meet their end through quantum nucleation, where a tiny bubble of true vacuum forms in their cores, expanding at light speed to convert the entire star into something even more exotic. What's left behind tells a haunting story. The magnetic fields that once dominated light years around the star get severed from their source, snapping like rubber bands and launching final bursts of energy. Any planets or companion stars orbiting the now vanished neutron star would continue their paths unperturbed. Gravity doesn't care whether its source is a 12-mile-wide neutron star or an infinitely small singularity. The only clue might be the sudden silencing of a once steady pulsar beam, leaving astronomers to wonder whether its light simply faded, or whether something far more final occurred. These silent demises remind us that even the universe's toughest objects have expiration dates. Yet in their passing, they create new cosmic mysteries, black holes with neutron star ancestry, potentially sporting unusual spins or magnetic properties that defy classification. Some theories even suggest certain disappeared pulsars might actually be dormant magnetars biding their time before flaring back to life. One thing's certain: the death of a neutron star isn't an ending, but the start of a new chapter in spacetime's grand story. Deep in the cosmos, celestial metronomes keep time with unimaginable precision. Pulsars, whose spinning cores are so stable they make Earth's finest atomic clocks look like dollar store wristwatches. These natural timekeepers don't just tick, they pulse with a regularity measured in trillionths of a second, maintaining rhythms that drift less than 1 second every 10 million years. Take PSRB 1937 plus 21, a millisecond pulsar whose rotation varies by just 1 part in 10 to the 15th power. To put that in perspective, if this pulsar were a clock, it would lose or gain only a single second over 300 million years, outperforming even the cesium atomic clocks governing global timekeeping. How do these spinning stellar corpses achieve such staggering precision? The answer lies in their absurd density. A neutron star's mass, packed into such a small volume, creates a gravitational grip so unshakable that nothing, not solar winds, not magnetic storms, not even collisions with stray atoms, can significantly alter its rotation. Imagine a fly landing on a spinning bowling ball. The effect is so negligible it's laughable. That's the stability these cosmic flywheels enjoy, their angular momentum locked in like a gyroscope forged in a supernova. Scientists don't just admire this precision, they harness it. By tracking pulsar rotations with radio telescopes, astronomers have conducted some of the most stringent tests of Einstein's general relativity. When a pulsar orbits another massive object, its pulses arrive at Earth with infinitesimal delays, evidence of space-time warping around its companion. The famous double pulsar system PSRJ 0737-3039, discovered in 2003, has confirmed Einstein's predictions to within 0.0005%, making it one of relativity's most triumphant validations. But pulsar navigation isn't confined to textbooks. NASA's pioneering sextant experiment on the International Space Station demonstrated how spacecraft could use pulsar X-rays as interstellar GPS beacons. By comparing arrival times of pulses from multiple pulsars, a vessel could triangulate its position anywhere in the galaxy with kilometer-scale accuracy, no ground stations required. It's like using lighthouse flashes to navigate an ocean, except these lighthouses are separated by thousands of light years and never burn out. The irony is delicious. The remnants of dead stars, once thought to be cosmic curiosities, now serve as the universe's ultimate chronometers. Their steady beats whisper secrets about spacetime's fabric, guide humanity's farthest journeys, and remind us that sometimes nature's simplest phenomena, a spinning sphere, a beam of light, hold the most profound utility. And somewhere out there, another pulsar waits to be discovered, its rhythms perhaps even more precise, its potential even more extraordinary. Even the most barren cosmic wastelands can hide surprising complexity. Take neutron star atmospheres, for example. These searing hot layers of gas cling to the surface like whispers against a storm, barely a few centimeters thick yet blazing at temperatures exceeding 1 million degrees. Unlike Earth's sprawling atmospheric blanket, a neutron star's gaseous shroud is so tenuous that standing on the surface would feel like staring into a vacuum, yet it's here, in these vanishingly thin layers, that X-ray telescopes uncover clues about the star's violent history and composition. The most common atmospheric suspects, hydrogen or carbon, stripped from interstellar material or leftover from the star's explosive birth. Picture a stellar phoenix wearing a ghostly cloak. As gas spirals toward the neutron star's surface, the star's gravity, billions of times stronger than Earth's, compresses it into a shimmering film thinner than a sheet of paper. What little atmosphere exists becomes ionized almost instantly, its atoms battered by radiation and magnetic fields until electrons are ripped away, leaving behind a plasma that glows fiercely in X-rays. Studying these wispy layers requires astrophysical detective work. When X-rays from the star's surface pass through its atmosphere, certain wavelengths get absorbed by elements present in the gas, a spectroscopic fingerprint revealing its chemical makeup. The Chandra X-ray Observatory, for instance, has spotted carbon-rich atmospheres on neutron stars like RX-Joan 856.5-3754. Where the gas acts like a cosmic stained glass window, filtering the star's radiation into distinct bands of color. Other stars, like the nearby J0325.6-2623, show hydrogen absorption lines, suggesting they've recently cannibalized gas from a companion or interstellar cloud. But these atmospheres aren't static. Magnetic fields stronger than Earth's by a trillionfold can peel away layers or trap them in glowing coronae, while bursts of radiation from starquakes blow off patches like solar flares. Some neutron stars even sport hotspots, localized atmospheric zones above their magnetic poles, wherein falling gas ignites in perpetual storms of X-rays. It's a precarious existence. One moment, the atmosphere clings to the surface. The next, a violent burst might eject it entirely, leaving the star naked until new material drifts close enough to be captured again. What fascinates scientists most isn't just the atmosphere's composition, but what it reveals about the star beneath. The way X-rays dance through these gaseous veils hints at surface temperatures, magnetic field configurations, and even crustal quakes. In that sense, these minuscule atmospheres act like cosmic tea leaves, their subtle patterns telling stories of a star's past, present, and eventual fate. And with every new observation, we're learning to read them more clearly, uncovering secrets written in light from the most extreme environments in existence. Lightning isn't just an earthly phenomenon. Imagine bolts of energy so powerful they could vaporize a planet, crackling across the magnetosphere of a neutron star like cosmic fireworks. These aren't your average thunderstorms, they're relativistic discharges sparked by magnetic fields trillions of times stronger than Earth's, twisting space itself into a particle accelerator. Picture the northern auroras, but instead of gentle solar wind particles painting the sky in pastels, think of electrons whipped to near light speed, slamming into the star's atmosphere with enough force to generate gamma-ray flashes visible across the galaxy. At the heart of this celestial light show is a process called magnetic reconnection. On Earth, this phenomenon powers solar flares and geomagnetic storms, but on a neutron star, the scale is incomprehensible. When the star's ultra-rigid crust shifts under magnetic stress like tectonic plates snapping during an earthquake, it sends shockwaves through the magnetosphere, violently snapping and reconnecting magnetic field lines. The energy released in these events doesn't just ionize atoms, it tears them apart, creating jets of plasma that spiral along magnetic highways, emitting X-rays and radio waves in pulses so intense they outshine entire star systems. Some of the most extreme examples come from magnetars, where these discharges reach almost mythical proportions. Take SGR 0526-66, a magnetar whose starquakes triggered gamma-ray bursts in 1979, so bright they bounced off the moon and saturated spacecraft detectors across the solar system. The event released more energy in a tenth of a second than our Sun will emit in 100,000 years, not from nuclear fusion, but from pure magnetic fury. What's startling is how familiar the underlying physics can feel. Just as lightning on Earth equalizes charge imbalances between clouds and the ground, neutron star discharges redistribute energy across their magnetospheres. But instead of water molecules colliding in storm clouds, it's electrons and positrons, antimatter counterparts to electrons, getting caught in the crossfire, creating annihilation bursts that flicker like strobe lights in the void. This isn't just theoretical. Radio telescopes have picked up lightning signatures from pulsars like the crab, where plasma waves ripple outward like the aftermath of a thunderclap. And in 2021, astronomers observed a magnetar flare from 13 million light-years away that mimicked the behavior of terrestrial lightning, just scaled up by a factor of a quadrillion. The similarities are uncanny. Both involve runaway particle acceleration, both emit radio static, and both leave behind glowing aftereffects, the key difference. Neutron star lightning doesn't just illuminate the sky, it rewrites the rules of high-energy physics. These magnetic maelstroms do more than dazzle, they shape the star's very evolution. Each discharge saps a bit of the star's rotational energy, like a cosmic brake pad made of pure radiation. Over millennia, this relentless tapping slows the star's spin, cools its surface, and may even determine whether it dies quietly as a fading ember or explodes in one final catastrophic flare. And somewhere in those crackling plasma currents, hidden in the chaos of collapsing field lines, might lie clues to how the universe itself harnesses magnetism to sculpt the cosmos. Among the countless neutron stars scattered across our galaxy, one stands out not for its extreme behavior, but its unsettling proximity. Meet Calvera, the closest known neutron star to Earth, lurking a mere 250 light-years away in the constellation Ursa Minor. To put that in perspective, if our Milky Way were the size of a football field, Calvera would be hovering just a few inches from our solar system. This cosmic neighbor wasn't discovered by its radio pulses or violent outbursts, but through its faint X-ray glow, a whisper of radiation betraying its presence in data from the Rosat satellite, like catching a predator's eyeshine in the dark. At first glance, Calvera seems unremarkable. No magnetar flares, no rapid spinning, just an isolated neutron star cooling quietly in the void. But its very normalcy is what makes it extraordinary. Most neutron stars this age should have faded beyond detection, yet Calvera burns brighter in X-rays than expected, as if it's clinging stubbornly to its youth. Some theories suggest it might be reheating itself through quantum processes in its core, while others propose it's secretly siphoning gas from an unseen companion or interstellar clouds. Whatever the reason, its abnormal glow is what allowed astronomers to spot it, a silent sentinel closer to us than any other of its kind. Now imagine if Calvera were even nearer, say within 30 light-years. At that distance, its soft X-ray emissions would still pose no threat, but any magnetic outburst would become a planetary emergency. A single magnetar-like flare could strip Earth's ozone layer within hours, exposing the surface to deadly ultraviolet radiation. Its gravity, though weak by stellar standards, would subtly perturb comets in the Oort cloud, potentially sending icy projectiles hurtling toward the inner solar system. And if it were as close as Alpha Centauri, the night sky would host a new, eerie pinpoint of X-ray light, pulsing faintly like a dying ember, a constant reminder of how lethal the cosmos can be. What's truly fascinating is how Calvera got here in the first place. Neutron stars are born from supernova, and those explosions typically give them tremendous kick velocities, up to 5 million miles per hour. Yet Calvera moves relatively sedately, drifting through the galaxy's halo rather than the star-rich disk where it likely formed. This suggests it might be much older than we think, having slowed over millions of years, or that its birth explosion was oddly symmetrical, failing to impart the usual stellar shove. Either way, its presence in our celestial backyard forces us to reconsider just how many of these stellar ghosts might be hiding in plain sight, undetected until the right telescope catches their faint, telltale glow. Calvera's discovery also hints at a larger population of radio-quiet neutron stars, objects too faint or misaligned to show pulsar beams, but close enough to reveal themselves through X-ray or gamma-ray emissions. Estimates suggest there could be hundreds of these stealthy remnants within a few thousand light-years of Earth, quietly cooling in the dark. Some might even be closer than Calvera, their radiation too weak for current instruments to spot. It's a humbling thought. We've mapped stars millions of light-years distant, yet stellar corpses could be drifting unseen right on our cosmic doorstep, waiting for sharper eyes to find them. So while Calvera poses no danger today, its existence is a reminder that the universe doesn't just operate on grand scales sometimes. Its most intriguing mysteries are hiding in the neighborhood, masquerading as ordinary until we look closely enough. And who knows what other celestial surprises might be lurking even nearer, just beyond the edge of our current vision. Hidden beneath the crushing gravity and blistering magnetic fields of neutron stars lies an unexpected talent these celestial powerhouses can sing. Not with melodies we'd recognize, but through pulses of radiation vibrating at precise frequencies, creating a cosmic symphony detectable across interstellar space. When a starquake rips through a neutron star's rigid crust, or when fresh matter crashes onto its surface, the entire structure rings like a bell struck by a hammer, sending oscillations reverberating through its ultra-dense interior. The resulting tones are far deeper than any human ear could perceive, with some frequencies lasting minutes between peaks, a bass note resonating across light years. Scientists listen to these vibrations using X-ray telescopes tuned to the star's electromagnetic emissions. Every quake or impact distorts the star's X-ray pulses like a fingerprint, revealing details about its internal structure. Take Jaro Jones 74.2-2808, a neutron star whose surface rippled after a violent outburst in 1996. NASA's Rossi X-ray Timing Explorer detected oscillations at 367 Hz, a pitch roughly equivalent to an F-sharp on a piano if it were played by a stellar corpse 12 miles wide spinning 8 times a second. These aren't random noises, they're the literal sound of space-time itself vibrating, with the neutron star's incredible density amplifying the tones into detectable signals. What makes these cosmic songs so valuable is how they expose the star's hidden anatomy. Different vibration modes probe different layers. Surface quakes produce high-frequency overtones, while deeper oscillations resonate like the lowest notes on a pipe organ. By analyzing these frequencies, astronomers can map the star's interior as clearly as geologists study Earth with seismic waves. Some vibrations even hint at the possible presence of exotic matter in the core, where neutrons might dissolve into quark soup under the extreme pressure, altering the star's harmonic signature. The most mesmerizing performers might be the accreting neutron stars in binary systems. As gas from a companion star spirals onto their surfaces, it doesn't just impact silently, it creates rhythmic X-ray pulsations that resemble a metronome ticking in time with the infalling material. These aren't random splashes, they're structured beats with the timing between pulses revealing the star's rotation speed and the intensity reflecting how much matter is raining down. Systems like XT Jones 710.3-176 have produced quasi-periodic oscillations where the X-ray flux rises and falls in patterns resembling a drum roll, a stellar cadence dictated by gravity's unrelenting grip. Yet these songs aren't eternal. Over millennia, neutron stars cool and their crusts thicken, damping the vibrations until the music fades into silence. Some particularly rowdy performers like the Magnetars might only sing during violent outbursts, their melodies lasting mere minutes before the star's magnetic field smothers the oscillations. But while the concert lasts, each note carries priceless information. Those deep, resonant frequencies are more than just cosmic curiosities, they're diagnostic tools, letting us eavesdrop on the universe's most extreme environments, one piercing X-ray note at a time. Neutron stars don't just bend the rules of physics, they smash them to pieces and leave scientists scrambling to pick up the fragments. Take something as seemingly simple as cooling. These stellar remnants should, by all rights, freeze into near absolute zero husks within a million years of their birth. Yet some neutron stars glow stubbornly with heat that defies every model, as if they've discovered a secret furnace in their cores. The Cassiopeia, a supernova remnant, for instance, hosts a neutron star that's cooling twice as slowly as predicted, its surface still roasting at over 2 million degrees Celsius despite being over 300 years old. It's like finding a cup of coffee left in the Arctic that hasn't just stayed warm, it's still steaming after decades. Then there's the enigma of what's actually inside them. We know the outer layers are a crystalline crust of iron nuclei squeezed into a lattice tighter than a diamond, but below that, the core might be a surreal menagerie of exotic particles. Under pressures so extreme that even atomic nuclei crumble, neutrons could dissolve into a sea of free quarks, the fundamental building blocks of matter normally locked inside protons and neutrons. Some theories suggest these quarks might pair up into superconducting states, flowing without resistance and generating magnetic fields that would make a Magnetar's fury look tame. Other models propose even stranger possibilities, like strange matter made of up, down, and strange quarks, a hypothetical substance so stable it could convert anything it touches into more of itself, like some cosmic zombie virus. But how do we test these wild ideas when the cores are buried under 12 miles of the universe's most impenetrable material? Nature provides cruel experiments. When neutron stars collide, their merger momentarily exposes the inner workings to telescopes and gravitational wave detectors. The kilonova explosion from the 2017 neutron star collision, for example, spat out gold and platinum at rates that only make sense if the star's cores were brimming with free neutrons, a hint that quark matter might indeed be lurking beneath the surface. Meanwhile, lab experiments on Earth, like those at CERN heavy ion colliders, try to recreate quark-gluon plasma, the primordial soup that might mimic neutron star interiors, but even these only scratch the surface of the energies involved. The greatest puzzle of all might be how these stars manage to exist at all. Pack that much mass into that smaller space, and general relativity says they should collapse into black holes. Yet neutron stars stubbornly cling to existence, balanced on a knife's edge between total collapse and explosive dissolution. Some might even be quark stars, in disguise objects so dense they've crossed a threshold where neutrons no longer exist as distinct particles, but the whole core has melted into a single gargantuan quark nucleus. It's a reminder that the universe isn't just stranger than we imagine, it's stranger than we can imagine, and neutron stars are its most brazen dare to our understanding. Every time we think we've got them figured out, they throw another curveball, whispering tantalizingly that the real answers might rewrite physics itself. Some neutron stars don't just lurk in isolation, they become cosmic vampires, slowly draining the life from their stellar companions in a gravitational heist that lights up the universe. Picture this, a dense stellar corpse locked in orbit with a hapless star, its immense gravity peeling away layers of gas like an invisible hand stripping fruit from a vine. This stolen material doesn't just vanish, it spirals toward the neutron star in a glowing disk of superheated plasma, a cosmic whirlpool so hot it blazes with X-rays visible across galaxies. These aren't gentle exchanges, they're full-scale assaults, with the donor star eventually paying the ultimate price for its neighbor's insatiable hunger. The mechanics of this theft are as elegant as they are brutal. As the two stars orbit each other, the neutron star's gravity creates tidal forces strong enough to warp its companion, stretching the star into a teardrop shape. Gas from the outer layers gets pulled across an invisible boundary called the Roche-lobe, the point where the companion star's gravity loses its grip and spills into the neutron star's waiting clutches. But this material doesn't fall straight in. Instead, it forms a swirling accretion disk, a glowing maelstrom where friction heats the gas to millions of degrees, turning it into a volatile engine of X-rays. Systems like Scorpius X1, the brightest X-ray source in the sky outside our solar system, are textbook examples of this celestial vampirism in action, their disks shining so fiercely they outshine the sun by tens of thousands of times. What happens next is a slow-motion tragedy. As the donor star loses mass, its core grows more exposed, and the neutron star's gravity tightens its grip. The once stable orbit shrinks, pulling the two stars into an ever tighter embrace, a death spiral that can last millions of years. In some cases, the neutron star's feast becomes so voracious that the accretion disk collapses under its own weight, triggering thermonuclear explosions on its surface. These X-ray bursts can erupt multiple times a day, each one unleashing in seconds what the sun radiates in a week. But the real horror show begins if the donor star is a red giant. The neutron star plunges into its bloated outer layers, orbiting inside the star itself like a parasite burrowing into its host, accelerating the companion's demise. Yet the vampire analogy only goes so far because sometimes the victim fights back. In rare cases, the stolen material doesn't just fuel the neutron star, it revives it. Old, slow-spinning neutron stars can become millisecond pulsars, their rotations whipped up to dizzying speeds by the incoming gas's angular momentum. It's a cosmic irony. The very material being stolen gives the predator new life, transforming it into a hyperactive beacon blinking hundreds of times per second. Meanwhile, the donor star, now stripped to a fraction of its original mass, may end its days as a smoldering white dwarf, or, if the neutron star's appetite is insatiable, get completely obliterated. These binary systems aren't just destructive, they're also cosmic laboratories. The accretion process creates conditions so extreme that atoms are ionized down to bare nuclei, and magnetic fields channel plasma into jets that shoot out at near light speed. Observing these interactions helps astronomers understand everything from black hole feeding habits to the origins of mysterious fast radio bursts. And perhaps most eerily, they remind us that even in the vastness of space, no star is truly safe, especially when a neutron star is nearby, hungry and waiting to feast. What if the pulsing signals from neutron stars aren't just natural phenomena, but deliberate signposts left by advanced civilizations? Some scientists speculate that precisely timed pulsar beams could serve as the universe's ultimate navigation beacons, engineered by extraterrestrial intelligence to mark important locations across the galaxy. This idea isn't as far-fetched as it sounds after all. Humans have already used pulsars as cosmic landmarks in our own attempt to communicate with alien life. The famous Arecibo message, beamed toward star cluster M13 in 1974, contained a clever pulsar-based map pinpointing Earth's location. The transmission's binary code included the relative positions of our Sun and key pulsars, their unique spin rates acting like fingerprints any advanced civilization could decode. Each pulsar's frequency served as a ticking clock, allowing recipients to triangulate our solar system's position, even if the message were intercepted millions of years later. It was humanity's version of throwing a stone into the cosmic pond, and the ripples we chose were neutron stars. Here's why pulsars make ideal interstellar signposts. Unlike stars that drift over time or variable stars that change brightness unpredictably, millisecond pulsars are nature's most precise chronometers, their pulses arriving with atomic clock regularity across millennia. An advanced civilization could deliberately alter a pulsar's emissions through orbital mirrors or magnetic field manipulation to encode information in subtle timing variations. Imagine a pulsar whose pulses suddenly shifted into prime number sequences or mathematical constants, a clear signature of artificial tampering. The concept gains weight when you consider pulsar planets, worlds orbiting neutron stars that somehow survived their host star's violent supernova. These resilient survivors might be prime real estate for civilizations seeking stable orbits near an energy-rich beacon. The pulsar PSRB 1257+12, for instance, hosts at least 3 planets, proof that life could theoretically exist in these extreme environments, protected by dense planetary magnetic fields from the neutron star's radiation. But the real breakthrough would come if we detected a pulsar signaling in patterns that defy natural explanation. Projects like SETI already monitor neutron stars for artificial signals hidden in their radio emissions. A telltale sign might be a pulsar emitting synchronized pulses across multiple frequencies, a feat impossible without intelligent intervention. Other red flags could include pulsars arranged in geometric patterns or emitting compressed data bursts resembling our own digital communications. Perhaps the most tantalizing possibility is that we've already received such a signal and missed it. In 2007, astronomers detected a powerful radio burst from a distant neutron star that lasted just 5 milliseconds yet contained energy equivalent to 500 suns. While likely natural, its extreme properties sparked debates about artificial origins. Future observations might reveal similar bursts with repeating patterns or embedded information, a cosmic hello encoded in the language of collapsing stars. Whether as navigational aids, communication hubs, or even remnants of ancient astroengineering projects, neutron stars could hold the key to finding our place in a galactic community. Their immutable rhythms cut through the noise of the universe like drumbeats in the dark, persistent, unmistakable, and waiting to be understood. And if we ever do crack their code, it might not just reveal the physics of extreme matter, but the neighbors we never knew we had. At the heart of the constellation Cetus, an ancient relic drifts silently through space, PSRJ 0108-1431. The oldest known neutron star in our galactic neighborhood. Clocking in at over 200 million years, this cosmic senior citizen has outlived entire species on Earth, spinning steadily while continents shifted and civilizations rose and fell below. What makes this pulsar extraordinary isn't just its age, it's how defiantly it refuses to fade into oblivion. Most neutron stars this ancient should have cooled into near invisibility, their magnetic fields withered to shadows of their former strength. Yet Pulsar J0108-1431 still pulses with detectable radio waves, its surface warmer than models predict and its magnetic field stubbornly persistent, as if it's discovered some secret loophole in stellar physics. The mystery lies in the numbers. Neutron star cooling theories suggest that after 100 million years, these objects should have shed most of their heat through neutrino emissions and surface radiation, settling into a deep freeze just above absolute zero. But this old-timer's X-ray emissions reveal a surface temperature around 1 million degrees far hotter than expected. One possibility is that residual nuclear reactions still simmer in its crust, fueled by dense layers of electron-capturing elements like iron slowly rearranging themselves under gravity's relentless crush. Another theory points to superfluid vortices in its core, quantum whirlpools that occasionally release stored energy like a battery leaking charge, providing just enough heat to keep the star from going dark. Then there's its magnetic field, which by all rights should have decayed to insignificance ages ago. Normally, neutron star magnetism fades as currents in the crust gradually dissipate like a fridge magnet left out in the sun. Yet this pulsar's field remains surprisingly robust, still channeling radiation into beams that sweep past Earth every 0.24 seconds. Some researchers speculate its crust might be unusually conductive, preserving electric currents like a superconductor with no expiration date. Others suggest the star's slow rotation compared to younger, hyperactive pulsars puts less strain on its magnetic architecture, allowing the field to maintain coherence far longer than busier counterparts. What's truly remarkable is how this lone object rewrites the textbook on stellar evolution. When astronomers compare Pulsar J0108-1431 to younger neutron stars, they're essentially looking at a time lapse of cosmic aging, revealing which processes endure and which fade with time. Its prolonged activity hints that the galaxy might be teeming with similarly ancient neutron stars we've missed, too faint for most telescopes but quietly persisting in the dark. Future observatories like the Square Kilometre Array could uncover more of these stellar retirees, painting a fuller picture of how neutron stars spend their twilight eons. For now, this pulsar serves as a living fossil, a testament to just how little we understand about the life cycles of the universe's most extreme objects. It whispers a tantalizing truth: even after 200 million years, a neutron star's story isn't over. It's just entering a chapter we're only beginning to read. When neutron stars devour their surroundings, they don't always consume everything. Sometimes they leave behind cosmic crumbs in the form of glowing rings. Take the Magnetar 4U0142+61, a spinning stellar corpse 3,600 light-years away with a bizarre accessory, a shimmering disk of debris orbiting its equator like Saturn's rings scaled down to a nightmare level. Unlike the icy hoops around gas giants, this ring isn't made of frozen water. It's likely the scorched remnants of a planet or asteroid torn apart by the Magnetar's gravity, reduced to a swirling band of dust and vaporized metals heated to thousands of degrees. The origins of these rings read like a demolition derby in slow motion. Imagine a rocky body drifting too close to the neutron star's gravitational maw. Tidal forces stretch it like taffy until it fractures, scattering fragments into a chaotic orbit. Over time, collisions grind the debris into finer particles, while radiation pressure from the star's furious energy output arranges them into a flattened disk. In 4U0142+61's case, infrared observations revealed the ring's presence through an unexpected glow thermal radiation from material too distant to be part of the Magnetars' immediate environment, but too close to have escaped entirely. What's startling is how these rings defy expectations. Neutron stars aren't supposed to retain debris disks. Their colossal gravity, intense radiation, and magnetic fields should obliterate or expel any surrounding material. Yet here they are, stubbornly persisting like smoke rings after an explosion. One theory suggests the Magnetars' monstrous magnetic field acts as a shield, trapping particles in a stable orbit like an invisible fence. Another proposes the disk replenishes itself through ongoing collisions, a self-sustaining demolition site where fragments continually shatter and reform. The real fascination lies in what these rings imply about survival in extreme environments. If planets or asteroids can leave traces around neutron stars, could their debris carry chemistry into the afterlife? Some models suggest these disks might even foster molecule formation, with vaporized metals condensing into exotic minerals under the star's harsh glare. It's a twisted form of cosmic recycling where the ruins of worlds become the building blocks for whatever comes next. And they're not just curiosities, these rings might solve a bigger mystery. The presence of dust around neutron stars could explain why some appear unnaturally bright in infrared light, their emissions previously chalked up to theoretical processes. Now we have a tangible culprit, scorching hot debris glowing like embers in the dark. Each ring is a forensic snapshot of destruction and persistence, proving that even in the universe's most hostile realms, matter finds ways to linger, if only as ashes around a stellar funeral pyre. Neutron stars crush entire suns into spaces no bigger than a bustling downtown. Imagine all of New York City squeezed into an area smaller than Manhattan. These cosmic marvels pack more mass than our sun into a sphere just 12 miles across, so compact that if you could drive around one at highway speeds, you'd complete the loop in under 15 minutes. To put that in perspective, Chicago's city limits stretch over 230 square miles, enough to fit nearly 500 neutron stars side by side. Yet for all their minuscule dimensions, the forces at play inside them are anything but small. What's truly mind-bending is how something so tiny can wield such gravitational might. Picture Earth's entire human population, nearly 8 billion people crammed into a single high-rise building. That's the level of density we're dealing with. A neutron star's matter is packed so tightly that a single grain of sand from its surface would outweigh a fully loaded freight train. This absurd compactness explains why they're invisible to optical telescopes despite their extreme energy. Unlike stars that blaze across light years, neutron stars emit most of their radiation as X-rays or radio pulses, detectable only with specialized instruments. Even the closest known neutron star, Calvera, appears 100,000 times fainter than the dimmest star visible to the naked eye, a whisper of radiation lost in the cosmic noise. Their small size also amplifies their most exotic behaviors. Magnetic fields that would spread weakly across a normal star become concentrated into unimaginable intensities when compressed into such a tiny package. A magnetar's field, powerful enough to distort atoms from thousands of miles away, owes its strength partly to this compression, like squeezing a bar magnet down to a pinhead. Similarly, their rapid spins, some completing hundreds of rotations per second, are only possible because of their compact form, where even slight changes in rotation speed can whip the surface at a significant fraction of light speed. Yet this tiny stature comes with cosmic camouflage. A neutron star drifting through our solar system would be nearly impossible to spot until it was practically on top of us. Its gravitational pull on planets might give it away before any telescope could catch its faint glow. When two neutron stars collided in 2017, their merger was detected 130 million light-years away only because of the gravitational waves they emitted. Optical telescopes saw nothing until the resulting kilonova explosion lit up. It's a cosmic irony. The universe's most dense objects are also some of its hardest to find, hiding in plain sight until their extreme physics betrays them. But that small size also makes them cosmic Rosetta Stones. Their compactness means every square inch is a laboratory for extreme physics, from the warping of space-time around them to the exotic matter hiding in their cores. If neutron stars were the size of actual cities, their gravity would be less overwhelming, their magnetic fields less intense, and their spins slower, making them far less useful for testing the limits of known science. Their power lies in their impossibility, a reminder that sometimes the universe's most revolutionary secrets come in the smallest packages. Some neutron stars don't just orbit their companions, they slowly annihilate them with a rain of lethal radiation, earning the grim nickname Black Widows. These cosmic predators spin at dizzying speeds, emitting beams of high-energy particles and gamma rays that act like a celestial blowtorch, systematically stripping away their partner star's atmosphere atom by atom. The most infamous example, the Black Widow pulsar PSRB 1957+20, has already reduced its companion to a fraction of its original mass, a mere husk of what was once a full-fledged star, now barely larger than Jupiter. The destruction happens with terrifying efficiency. As the pulsar spins, its intense magnetic field accelerates charged particles to nearly the speed of light, creating a relentless stellar wind that bombards the nearby star. This isn't just gentle erosion, it's a full-scale assault, with radiation pressure tearing molecules apart and blasting the debris into space. Over millions of years, the companion star loses its outer layers, leaving behind a scorched core that may eventually vanish entirely. In the case of the Black Widow pulsar, the victim has been whittled down to less than 2% of the Sun's mass, a tragic testament to the neutron star's destructive power. What makes these systems especially fascinating is the warped dance they perform. The pulsar's radiation doesn't just evaporate the companion, it also heats the star's remaining gas to extreme temperatures, creating a glowing tail of ionized material that streams away like a comet. This doomed star isn't just fading quietly, it's being actively dismantled in real time, its death throes visible across the electromagnetic spectrum. Some Black Widow systems even exhibit day and night sides on the companion, one hemisphere perpetually scorched by the pulsar's fury, the other locked in frigid darkness. The irony is that the companion may have once been the neutron star's lifeline. Many Black Widow systems started as low-mass X-ray binaries, where the pulsar fed on material siphoned from its partner, spinning faster as it gorged on stolen gas. But like a parasite that outlives its host, the pulsar's appetite eventually turns fatal. Now, instead of nourishing the neutron star, the companion is being vaporized by it, a cosmic case of biting the hand that once fed it. Yet, even in destruction, these systems offer scientific gold. The evaporating material acts like a cosmic windsock, revealing the pulsar's particle output in stunning detail. By studying how the companion's remnants glow in X-rays and radio waves, astronomers can measure the pulsar's spin-down energy, magnetic field strength, and even the composition of its deadly stellar wind. It's a morbid trade-off. A star dies, but in its demise, it illuminates the physics of one of the universe's most extreme phenomena. The Black Widow pulsar won't stop until its partner is gone entirely, and when that happens, the system will transform yet again. The pulsar, now alone, will drift through space as a millisecond pulsar, its rotation unnaturally sped up by its long-ago feast. Its victims' scattered atoms, meanwhile, will join the interstellar medium, perhaps one day becoming part of new stars or new prey for another cosmic predator. The universe has a way of recycling tragedy into opportunity, and Black Widow pulsars are its most ruthless agents of change. Einstein's theory of relativity isn't just abstract math, it becomes a dazzling light show when a neutron star takes center stage. These ultra-dense objects don't just warp space with their gravity, They twist it into a lens, bending light from distant stars and galaxies into glowing halos and rings around them. Picture sunlight filtering through a glass ashtray, casting intricate circular patterns on a table, except here, the glass is space-time itself, and the patterns are cosmic mirages visible across interstellar distances. This phenomenon, called gravitational lensing, transforms neutron stars into nature's own telescopes, magnifying and distorting whatever lies behind them in ways that reveal secrets no ordinary observation could uncover. One of the most striking examples is the neutron star RX Joan 856.5-3754, whose gravity sculpted the light of a background star into a perfect Einstein ring, a luminous circle hovering around the star like a halo forged by gravity itself. Named after Einstein's prediction that massive objects would bend light into such shapes, these rings aren't just beautiful curiosities, they're precision tools for weighing neutron stars. By measuring the ring's size and brightness, astronomers can calculate the star's mass with unparalleled accuracy, almost like placing it on a cosmic scale. When RxJ's ring flickered due to a companion star's motion, researchers pinned its mass at 1.4 solar masses, a critical date, a point in the debate about how compact neutron stars can get before collapsing into black holes. But the real magic happens when multiple rings appear. Some neutron stars positioned directly in front of distant galaxies don't just create one ring, they generate concentric circles, like ripples from a pebble dropped in a pond. Each ring corresponds to light bent at different angles, offering a layered snapshot of both the foreground star and the background galaxy. It's a cosmic matryoshka doll, with each layer revealing new details. The neutron star's mass warps the innermost ring most dramatically, while outer rings trace the fainter edges of the lensed galaxy. In rare cases, like with the neutron star Pulsar J0700-6618, these stacked rings even expose the galaxy's structure, highlighting spiral arms or dust lanes that would otherwise be too faint to see. What makes lensing so invaluable is how it bypasses the limitations of traditional astronomy. Normally, measuring a neutron star's mass requires detecting its gravitational influence on a companion, a method that only works if the star isn't isolated. But gravitational lensing doesn't care about companionship. It works even on lone neutron stars drifting through the void. When the nearby neutron star Calvera briefly lensed a background quasar, astronomers got its mass estimate purely from the quasar's distorted light, no binary system required. This technique is so precise it can even detect planets around neutron stars, should any exist, by the telltale wobbles they'd imprint on the lensed rings. Yet the most profound revelations come when lensing exposes the invisible. Dark matter's gravitational tug subtly alters Einstein rings, and neutron stars acting as lenses can map its distribution in ways other methods can't. In 2022, the lensed light around a neutron star in the Draco constellation revealed a dark matter filament no telescope could see directly, proof that these stellar remnants aren't just subjects of study, but tools for probing the universe's deepest mysteries. Every distorted ring, every stretched arc of light, is a reminder that even in the darkest corners of space, the universe finds ways to show us what's hiding in plain sight. Deep inside a neutron star, where pressures reach 100 trillion times Earth sea level, protons might be doing something extraordinary, flowing without resistance like electricity in a perfect wire. This isn't just theoretical speculation. It's a hypothesis that could solve two of neutron stars' biggest mysteries: their monstrous magnetic fields and those puzzling rotational hiccups called glitches. Picture the star's core as a quantum playground where protons pair up in a superconducting state, forming a frictionless fluid that generates and sustains magnetic fields strong enough to warp atoms from light years away. How does this quantum sorcery work? In ordinary materials, superconductivity occurs when electrons couple up, overcoming electrical resistance. But in a neutron star's core, protons normally trapped inside atomic nuclei might break free and form analogous pairs. Crushed together by the star's immense gravity, these protons could condense into a superfluid, their coordinated motion creating persistent electric currents. Since magnetic fields arise from moving charges, these endless proton currents would act like a cosmic electromagnet, amplifying the star's magnetic field to ludicrous strengths without any energy loss. Magnetars with magnetic fields 1,000 times stronger than typical neutron stars might owe their fury to particularly robust proton superconductivity in their cores. But there's another layer to this story: neutron superfluidity. While protons may superconduct, the star's abundant neutrons could flow without viscosity, creating microscopic whirlpools called vortices. Normally, these vortices latch onto the crust, spinning in sync with the star. But when the superfluid's rotation lags behind the crusts, the vortices suddenly snap free, transferring angular momentum to the surface in a violent jerk, a glitch. It's like spinning a bucket of water. When the water catches up to the bucket's motion, the whole system lurches. This phenomenon might explain why some pulsars abruptly speed up, their rotations hiccuping by fractions of a second. The evidence, observational clues like sudden temperature drops in young neutron stars hint at superconductivity kicking in as the core cools, and glitches often coincide with X-ray flares, suggesting crust fractures linked to superfluid vortices breaking loose. Theories even predict distinct glitch families, some caused by proton superconductivity disrupting magnetic fields, others by neutron vortices rearranging, each leaving unique fingerprints in the star's spin behavior. Yet mysteries remain. If protons superconduct, why don't all neutron stars become magnetars? Could quark matter in the core alter or suppress superconductivity? Every glitch, every magnetic outburst is a data point in this cosmic experiment, teasing us with answers that might rewrite our understanding of quantum physics under conditions no lab could ever replicate. And buried in those answers could be something even wilder: the possibility that neutron stars aren't just superconducting, but hosting superconductivity in forms we haven't even dreamed of yet. Some of the universe's most elusive secrets might be hiding in plain sight, crushed inside neutron stars. While we've long searched for dark matter in distant galaxies or underground detectors, these ultra-dense stellar remnants could be quietly manufacturing it right under our noses. Imagine the scene deep within a neutron star's core, where pressures are so extreme that protons and neutrons themselves begin to break apart. In this subatomic pressure cooker, collisions between particles could reach energies rivaling the earliest moments of the Big Bang, precisely the conditions theorists speculate might give rise to dark matter particles. The math is tantalizing. When two neutrons smash together with enough force, they might briefly form exotic particles that don't interact with ordinary matter actions, sterile neutrinos, or other hypothetical dark matter candidates. Unlike fleeting particle collisions in Earth-based accelerators, a neutron star's relentless gravity could trap these dark matter particles inside, allowing them to accumulate over millennia. Some calculations suggest certain neutron stars could contain dark matter concentrations millions of times denser than the halos surrounding galaxies, a hidden payload slowly altering how the star cools, spins, or even collapses. This isn't just speculation. Observational clues hint at something strange happening inside neutron stars. Take the case of a neutron star called Hess-Jones 7 3-247, whose surface temperature is mysteriously cooler than models predict. One possible explanation: dark matter particles interacting with regular matter could carry away extra heat, acting like a cosmic refrigerant. Similarly, certain pulsars exhibit spin-down rates that don't match theoretical predictions, an anomaly that could reflect dark matter dragging on their interiors like invisible molasses. The implications are staggering. If neutron stars truly produce or concentrate dark matter, they could solve two cosmic puzzles at once: First, they'd explain where a fraction of the universe's missing mass resides trapped inside these stellar graves. Second, they'd give astronomers a natural laboratory to study dark matter's properties by observing how it changes neutron star behavior. When the LIGO Observatory detected gravitational waves from colliding neutron stars in 2017, some physicists scrutinized the data for signs of dark matter's influence on the merger, perhaps an anomalous energy loss or unexpected afterglow. But here's the twist. Neutron stars might not just harbor dark matter, they could be destroying it too. In scenarios where dark matter particles are their own antimatter counterparts, collisions in the star's core could annihilate them, releasing energy that keeps ancient neutron stars warmer than expected. This process could explain why some pulsars like Pulsar J0108-1431, the ancient neutron star we discussed earlier, stubbornly retain heat despite their advanced age. Their prolonged warmth might be the smoking gun of dark matter's hidden activity. The search for these cosmic dark matter factories is already underway. Telescopes are scanning neutron stars for unusual X-ray emissions that might betray dark matter interactions, while gravitational wave detectors listen for telltale frequency shifts in merging systems. Future missions like the European Space Agency's Athena X-ray Observatory could analyze neutron star atmospheres for chemical anomalies caused by dark matter decay products. And buried in all that data might be the answer to one of astronomy's greatest mysteries, not just the nature of neutron stars, but the invisible scaffolding holding galaxies together. What makes this possibility so electrifying is how it turns our understanding inside out. Dark matter, long thought to dominate vast cosmic voids, might actually thrive in the most extreme particle colliders the universe has to offer, the crushed hearts of dead stars. If proven true, it would mean neutron stars aren't just exotic physics experiments, they're cosmic alchemists, transmuting the familiar into the mysterious right before our eyes. And that revelation could rewrite not just stellar physics, but our very comprehension of what fills the universe's shadowy corners. At the heart of an ancient globular cluster 28,000 light-years away, nature's ultimate cosmic top is spinning at speeds that defy comprehension. Pulsar J1748-2446 AD holds the undisputed title of fastest known neutron star, completing an astonishing 716 full rotations every single second. To put that unfathomable speed into perspective, if this pulsar were the size of a grapefruit, its equator would be whipping around at 24% the speed of light, covering nearly 45,000 miles in the time it takes you to blink. That's fast enough to circle Earth's equator almost twice before your heartbeat finishes a single cycle. How does something with the sun's worth of mass avoid tearing itself apart at these ludicrous speeds? The answer lies in neutron star physics at its most extreme. Every rotation subjects the star's surface to centrifugal forces equivalent to 10 billion times Earth's gravity, enough to vaporize any known material instantly, if not for two saving graces. First, the star's incomprehensible density creates gravitational binding energy so powerful that escaping its grip would require reaching 70% light speed. Second, its crystalline iron crust, a lattice of nuclei packed tighter than bullets in a firing line, possesses tensile strength 100 trillion times greater than steel. Even at these speeds, the crust bends but refuses to shatter, warped into an oblate shape where the equator bulges slightly from the spin while the poles remain crushed inward by gravity's unrelenting squeeze. The real marvel is how this cosmic speed record came to be. Unlike young pulsars born spinning fast then gradually slowing, Pulsar J1748 owes its breakneck rotation to a stellar partner it's been cannibalizing for eons. As gas from its companion star spiraled onto the neutron star's surface, the transferred angular momentum acted like a cosmic whip, accelerating its spin like a figure skater pulling in their arms, except here, the arms are entire solar masses of infalling plasma. This vampiric feast transformed what was once an ordinary pulsar into a millisecond powerhouse, its magnetic field funneling stolen material into jets that now blaze across radio telescopes as perfectly timed pulses. Yet even this extreme rotation has limits. Models suggest that neutron stars physically can't spin faster than about 1,000 revolutions per second without crossing a catastrophic threshold. At that point, centrifugal forces would overwhelm gravity's grip, potentially triggering one of two apocalyptic scenarios. Either the star flings its outer layers into space in a violent equatorial eruption, or if the spin-up continues, it reaches a point where space-time itself can't keep up, causing the star to collapse into a black hole mid-rotation. Pulsar J1748 hovers tantalizingly close to this theoretical maximum, its existence proving that nature can flirt with destruction on scales human engineering could never approach. What's perhaps most astonishing isn't the star itself, but how we detect it. The pulsar's lighthouse-like radio beams sweep past Earth every 1.39 milliseconds with timing so precise they rival atomic clocks in regularity. Each pulse arrives packed with information about the star's wobble, magnetic field fluctuations, and even the interstellar medium it traversed, data that lets astronomers measure its speed down to trillionths of a second. This precision turned the pulsar into a gravitational laboratory, confirming Einstein's prediction that rapid rotation should warp spacetime into a vortex around the star, an effect now called frame dragging. So while Pulsar J1748-2446 AD might look like just another flicker in the cosmic static, it's actually a boundary-pushing experiment in extreme physics, one where gravity, quantum mechanics, and relativity collide at speeds that stretch our understanding of the possible. And somewhere in the universe, another neutron star might be spinning even faster, waiting to be discovered and to rewrite the rules once again. Neutron stars don't just destroy stars, they devour planets whole, tearing them apart in a gravitational feeding frenzy that makes Jupiter's great red spot look like a summer breeze. The unfortunate worlds orbiting too close to these stellar zombies face annihilation, their rocky bodies shredded into spiraling streams of molten debris before being consumed atom by atom. Take Pulsar B1257+12, a pulsar 700 light-years away with a chilling legacy. It's the first neutron star ever found with planetary remains in its grasp, a ghostly testament to the carnage these cosmic predators leave behind. The process begins with tidal forces so extreme they defy earthly comparison. Imagine a planet like Earth drifting within a few million miles of a neutron star, close enough that the star's gravity pulls harder on the planet's near side than its far side. This difference stretches the planet into an elongated shape like taffy in the hands of a giant until the forces overwhelm its structural integrity. Rock melts, mountains crumble, and the entire world fractures into a ring of debris spiraling inward. For gas giants, the horror unfolds even faster. Their atmospheres are stripped away first, forming a glowing accretion disk around the neutron star, while their cores are splintered into asteroids that rain down in fiery streaks. Pulsar B1257+12 offers a forensic snapshot of this destruction. Astronomers discovered 3 small, jagged objects orbiting it, not intact planets, but the charred remnants of what might have been a full planetary system before the star's supernova explosion and subsequent gravitational tantrum. These survivors, dubbed Draugr, Poltergeist, and Phobter, are likely the dense cores of once larger bodies, their outer layers vaporized by the pulsar's radiation or ripped away by its gravity. Draugr, the innermost, weighs just twice the mass of our moon but orbits its undead host in a mere 25 days, so close that its surface is bathed in enough X-rays to liquefy titanium. What's eerie is how this necrotic system mimics the architecture of living solar systems. The remnants orbit in neat, near-circular paths, suggesting they reformed from debris after the initial destruction, a macabre reincarnation of planets from their own ashes. Some theories propose these objects might even be second-generation worlds, coalescing from the very material their neutron star parent devoured earlier. It's a cosmic Ouroboros, creation from destruction, new worlds born from the corpses of old ones. But not all planets face instant obliteration. Some resist, clinging to unstable orbits where the neutron star's gravity and radiation wage war on their chemistry. In 2016, astronomers spotted a potential survivor, a super-Earth candidate orbiting the pulsar J1719-1438, enduring despite a 4,000-degree surface temperature and hurricane-force stellar winds. How its sheer density might give it fleeting resistance, like a steel pebble in a furnace. But even this tough customer is doomed to eventually crumble under the neutron star's relentless appetite. The aftermath of these feasts lingers for eons. Swirling disks of pulverized planetary material glow in infrared around neutron stars like 4U0142+61. Their spectral lines revealing the fingerprints of vaporized basalt, iron, and even diamond, the shattered remains of alien geology. These disks aren't just graveyards, they're also nurseries. The same processes that destroy planets might seed new ones as dust particles collide and stick together in the neutron star's frigid outskirts, building bizarre, irradiated worlds unlike anything in our solar system. So while Pulsar B1257+12's ghastly entourage might seem like a cosmic oddity, it's actually a preview of Earth's distant future. When our sun dies, it too will leave behind a dense remnant, a white dwarf if we're lucky, or perhaps a neutron star if a neighboring giant star goes supernova. Either way, the inner planets won't survive the transformation. The lesson is written in the rubble around these stellar ghouls. In the universe's grand timeline, even worlds are fleeting, and neutron stars are the hungriest gravediggers of all. The cosmic hunt to unravel neutron star mysteries is entering its most thrilling chapter, yet thanks to a new generation of telescopes and observatories designed to probe these dense stellar remnants like never before. Leading the charge is NASA NICER, a softball-sized X-ray instrument mounted on the International Space Station that's already revolutionizing our understanding of extreme matter. NICER doesn't just observe neutron stars, it dissects their X-ray emissions with stopwatch precision, mapping the bizarre topography of their surfaces down to millisecond flickers. In 2019, it used Pulsar J0030+0451's X-ray pulses to calculate the star's mass and radius simultaneously, a breakthrough that narrowed down the equation of state for ultra-dense matter, essentially telling us how squishable or rigid neutron star cores really are. But NICER is just the opening act. The upcoming Laser Interferometer Space Antenna, or LISA, will take the search to uncharted territory by detecting gravitational waves from neutron star mergers at frequencies ground-based observatories can't reach. While LIGO catches the final, violent moments when neutron stars collide, LISA space-based sensors will monitor their slow-motion dance years or even decades before impact, tracking how their orbits decay as they radiate gravitational energy. This could reveal whether neutron stars are perfect spheres or slightly lumpy, a detail that sounds trivial but would reshape theories about their internal structure. Even more tantalizing, LISA might spot hypermassive neutron stars, fleeting hybrids that briefly form during collisions before collapsing into black holes, offering a glimpse of matter teetering on the edge of oblivion. Meanwhile, the European Space Agency's Athena X-ray Observatory, launching in the 2030s, will study neutron star atmospheres with spectroscopic precision, analyzing how their intense gravity bends light to weigh them more accurately than ever. Its targets include magnetars like SGR 0526-66, where Athena could detect quantum electrodynamic effects in the star's magnetic field, conditions so extreme they warp the very vacuum of space. And on the radio side, the Square Kilometre Array will scan millions of pulsars in unison, transforming them into a galaxy-wide gravitational wave detector. By monitoring subtle timing shifts in their pulses, this mega telescope could catch ripples from supermassive black hole mergers, revealing how neutron stars serve as interstellar seismographs. What makes these missions extraordinary isn't just their technology, it's the secrets they might pry loose. Neutron stars could hold clues about the universe's first seconds after the Big Bang, when matter was similarly crushed into quark-gluon plasma. Some theories suggest their cores might harbor strangelets, hypothetical particles that could unlock the nature of dark matter. Others predict they generate ripples in spacetime's fabric at frequencies we've yet to detect, cosmic vibrations that could confirm or reframe Einstein's relativity. The most electrifying possibility, these observatories might stumble upon phenomena we haven't even imagined yet. Before pulsars were discovered in 1967, no one predicted stellar corpses could pulse with such clockwork precision. Before gravitational waves were detected, merging neutron stars were just theoretical curiosities. As NICER, LISA, and their successors peer deeper into these cosmic extremes, they're not just answering old questions, they're handing us a new set of mysteries, written in gravity, light, and the whispers of matter pushed past its breaking point. And somewhere in that data, hidden in the flicker of an X-ray or the tremor of a spacetime ripple, might lie the next revolution in how we understand the universe itself. From their birth in supernova explosions to their role as cosmic gold factories, neutron stars have proven themselves as the universe's ultimate physics laboratories. We've seen how they spin faster than blender blades, warp spacetime into gravitational lenses, and generate magnetic fields strong enough to atomize matter from thousands of miles away. These stellar remnants don't just bend the rules, they rewrite them, crushing entire suns into city-sized spheres where matter takes forms we can't replicate on Earth. Whether it's the pulsar precision that rivals atomic clocks, the magnetar flares that outshine galaxies, or the gravitational waves they emit when colliding, neutron stars continually challenge what we thought possible. Consider the sheer range of extremes we've explored: surface gravity so intense it accelerates objects to millions of miles per hour in a single meter, cores where neutrons dissolve into quark soup, and temperatures hotter than the universe's first moments. These aren't just abstract concepts, they're real phenomena playing out in the cosmos right now, with neutron stars acting as both actors and stages for nature's most dramatic experiments. Their collisions forge the gold in our jewelry, their magnetic fields sculpt interstellar space, and their faintest vibrations carry secrets about quantum physics that laboratories could never uncover. Yet for all we've learned, these distant stellar corpses remain full of mysteries. What truly happens inside their cores? Could some harbor portals to exotic phases of matter? And what undiscovered phenomena might emerge when we observe them with even more advanced telescopes? The answers won't just satisfy curiosity, they could redefine our understanding of reality itself. So keep looking up. Every flicker of light from these cosmic extremes is a message in a bottle waiting to be decoded. Whether you're an aspiring astronomer or simply someone who marvels at the night sky, remember, the universe's greatest discoveries often come from the most unexpected places. And if neutron stars have taught us anything, it's that the wildest truths are still out there, hidden in the dark, just beyond the edge of what we think we know.